Hello.
Hello.
Yeah, so you can hear me?
Yes, sir.
Okay, so before we start this class, is there any doubts, questions about whatever has been done so far? Nothing about the dynamic programming problem. You guys are all comfortable with that?
Sir.
Yeah.
Sir, I have one basic question in dynamic programming. Sir, like, can we proceed from the, sir, in the last class, in the final step, you constructed a n cross m table.
Right.
So, sir, means can we use some algorithm to construct that table first, and can we then construct the recurrence, or we have to always go from recurrence to that table?
I mean, how will you fill up how will you fill up? I mean, in terms of the designing of the algorithm, you mean? In terms of designing of the algorithm, how will you, how will you know which table to fill or how to fill up the entries of the table unless you have the recurrence in your mind?
Okay.
Recurrence is used to fill up the entries of the table.
Yes.
Yeah. Any questions? Any other questions? Doubt? So, okay. So if you don't have none of you have any doubts and all, so let us jump into today's uh, topic. So it will be again dynamic programming, and we will be looking at another two problems. And this time I would try to give you time so that you guys can think about how to solve it. And that will be kind of the basic of this whole today's class. It will be more like a tutorial in some sense rather than a class. Uh, so okay, so we will be looking at two problems. First, we'll look at this problem of edit distance. So what is edit distance? So basically, so you have been given two sequence of symbols, so kind of two strings you can think of. And the question is that how many edits do you need to make to convert one to the other? So this is a very, very important question that happens again in many, many applications. Okay. Now, of course, it comes down to what do I mean by an edit? So the standard thing is that, okay, so you are allowed to do the following three edits. Number one, you can delete a bit or symbol rather. Okay, you can delete one of the letters, or you can add a letter anywhere you want. Okay, or you can change a letter. Okay, so let's see, for example, here. So here are these two words. First string is say snowy, SNOWY, and the next string is the sunny, SUNNY. So of course, if I want to convert snowy to sunny, I can do a sequence of 10 operations that will certainly give me change snowy to sunny. What is it? One after another, delete all the letters of snowy. So that will cost me 5 such operations, right? I have to delete 5 things. And then I can I can kind of keep on add one by one SUNN and Y. So by adding those letters, I will be able to get sunny. So first delete all the 5 of these letters of snowy, and then add all the letters of sunny, and the total number of operations is basically 5 deletes and 5 additions, and total is 10. Now, can I do more? Now, can you do it in less number of operations? Of course, I can, right? Okay. So what can I do? So the first thing I can do is that I can just, instead of changing, I can just blindly replace each of the letters with the other one. So I replace S with S, N with U, O with N, W with N, and Y with Y. So instead of deleting and then adding, I can just replace the letters, and that would cost me 5 replacements. So basically 5 operations, and I will be able to convert Snowy with Sunny. Now, of course, you can see that, oh, maybe I can do something even better, right? And that is obvious to see because, of course, S and Y are not to be changed. So they are there. So all I need to do is that I have to change N, then I will change O, and then I will change W. Right? Wonderful. So with 3 operation changes, I can do this. Now, can I do something else? Is there any more efficient way of doing it? Now, of course, there is another way of doing it is that I will say I want to convert Snowy to Sunny, right? I will delete O. Okay. So if I delete O, then what happens? It becomes SNWY. Now I can insert U before N. So that will become SUNWY. And then I will replace W with N. So it becomes SUNNY. Once again, with 3 operations now also, 1 addition, 1 deletion, and 1 change, I am able to convert Snowy to Sunny. Okay. So the minimum number of operations that is needed to change a particular string to another particular string is what is called the edit distance. Is the problem clear?
Yes, sir.
Okay. So let's maybe go for another example. So here, so I have a string exponential and a string polynomial. Can somebody quickly tell me some nice things through which you can change something?
We can remove EX,
Yeah,
push PO to the left,
right.
and put LY in that place.
Okay, so 4 operations.
It's 4. N stays, so not a problem. We remove E and N and we replace it with O and M.
Okay, so that is 2 operations again. So
Oh, we remove T also, sir. We remove T also. Sorry.
and the third operation. So with 7 operations, we can convert exponential with polynomial. Now, is this the best?
Let me think, sir.
I mean, I also don't know, honestly speaking, the answer of this particular thing. Okay, so whatever. So you understand the problem, and this is the problem, right? And the goal is to find out the minimum. Okay, so it has the applications again in a lot of things in biology kind of stuff, because again, you kind of how many changes that you have to make to get change one to the other. It has actually many other things. It has applications in graph theory. It has applications in data management. It has a huge amount of applications. I mean, this is just 2 applications that it has a massive set of applications. In fact, I mean, there are some generalizations of this very problem to other things like tree edit distance and graph edit distance and so on and so forth. Okay, but so the formal statement is that you have given 2 strings, A1 to AN and B1 to BM, and the smallest set of edits that can change A1 to AN to B1 to BM. Now, let me give you a couple of minutes. Why don't you guys try to solve it? Why don't you try to think about it? So if you have got some ideas, you can just unmute yourself and shout out.
Sir, like you are asking how to convert A1 to AM to B1 to BM, algorithm for that.
No, the minimum number of steps required to convert. Okay, what is the minimum number of edits that will convert that through by which you can convert A1 to AN to B1 to BN? Okay, so I mean minimum number. I mean maybe coming up with yeah, finding the exact set of edits also might be a useful thing to do. Any idea? Anything? Doesn't have to be dynamic programming, recursion, nothing. Can you come up with any idea? Can you give me any upper bound?
Sir, can we determine the the longest common subsequence between the two strings, because those characters
Okay, that you can
will
do.
remain-
So we know how to do that. Okay,
will
fine. And
remain
then,
constant, yeah. And then like for example, I'm converting exponential to polynomial, like taking the previous example. So there the substring would be longest substring POIAL. So these these 5 characters will remain constant. Rest I have to, that means edit 5 more characters from like the word exponential. But in the exponential thing, I have 6 characters remaining. So 5, I guess, changes and 1 deletion might do.
I mean, okay, you can. No, that is a. I mean, I would call that one more like a heuristic algorithm. Okay, you are saying that the longest common subsequence need to be remained intact,
Yes.
right? I mean,
Yes.
there is. I mean, I don't see a reason why that is necessarily true. Maybe it is, but then we need to kind of convince ourselves that okay, the longest common subsequence first of all needs to be. I mean, in the smallest one, the longest common subsequence has to be even same.
Yeah.
And even if we can find out a longest common subsequence, I mean, first of all, there might be many, so maybe we can find out only one of them, right?
Yes.
And then what? See, I mean, like longest common subsequence is not a very good option, okay?
Okay.
Because say if I think of this two sets, okay, two strings BOR AT, say, okay, BOR
Are
AT.
you writing something like?
No, I'm not
we
writing.
can- Oh, okay.
I can write, but I'm not writing. I'm just thinking of it from the top of my head. Okay, so it's- right? Hmm. Yeah, so I mean, what I wanted to kind of say is that the location of those longest common subsequence, I mean, there may be multiple longest common subsequence, right?
Yes.
And
Yes.
a particular one might be better suitable than the other.
Okay. Yeah.
Yeah, so something like if I think of this one, okay, B O A R T and B R E I T. All right.
Sir, we are changing the first one to second one.
I'm changing first one to second one. Okay.
Okay.
Actually, this is not so right. So, what is the longest common subsequence here? Longest common subsequence is B R T,
Yes.
right? So you
Yes.
want to keep them same. B
Yes.
R T. So what is the
Oh,
way
the
to convert this to this? So the idea will be okay, delete
OA,
O and A,
delete
add
A, add E.
EI. So total number
Yes.
of things is 4.
4.
But actually you can see that there are only 3 operations with which you can do that, right?
Yes. Yeah.
You can just convert O to R, A to E, and R to I.
Yes, sir.
So just longest common subsequence is not going to necessarily, I mean, it can take you to a different direction. I mean, it force your hands.
Okay. Okay.
So this is a good example of how a heuristic, something that sounds right, okay, might work or seems like fine, but actually you don't have a proof of it, and therefore it, I mean, and it might, the intuition might be wrong,
Okay, sir. I get it.
right?
Yes, sir.
So okay, so start. So if we have to start with this one, the simplest one that we can think of is also consider all possible sequences of edits and find the maximum, the minimum of them. Okay, which of them work? Now there is of course one problem. Just if I say that, oh, go and find out all possible sequences of edits that can convert one string to the another, that is possibly unlimited, right? This is why it is true that this is unlimited, but you can also kind of upper bound it a little bit also, because we know that there exists a operation which is max of say M and N, right? That is basically an upper bound on the edit distance of 2 strings, right? So max of M and N is a upper bound on the edit distance of the 2 strings. And how many operations are there which are at most max of M and N? Hello.
No, I didn't get you. So what did you say? Hello?
Yeah.
What?
Okay. Okay. How many operations are, how many possible set of edits are there, but the number of edits is 100? If I'm allowed to make, if you are allowed to make 100 edits, right? What is the maximum number of, what is the maximum number, and what is the maximum number of possible set of edits that are there?
3 to the power max of M.
Or which of what to the power?
3 to the power.
3 to the power that number, right? That's right. Why?
Yes.
Because the first edit can be either delete, add, or something. Okay, now that is not exactly correct. It's a bit more than that. Why? The first operation can be delete. You can delete any of the n options, right? Second option can be add. That can be added at any one of the n options, right? And third one is change. Again, the change can be of any one of those options, and you can change it to anything of the possible. So the total number is actually something like not 3, but 3n or something like that. Is it clear?
Yes, sir. Yes.
Right? So
Yes,
it is
sir.
not just three operations, that three possible operations. There are a bit more of them, 3n of them or something like that. But again, but still the total number of such operations, therefore, or total number of possible sequences is 3n to the power minimum of or maximum of n plus n, right? And which is fine. That's an upper bound. So at least by brute force, with a little bit of cleverness, you would be able to upper bound or come up with some algorithm. It's an exponential time algorithm, but some algorithm. But question is that, can we do better than that? Can we come up with a less than exponential time algorithm? And of course, the main idea is using recursion. And this is something that we have done over and over again. I don't know if you guys came up with anything of this kind of sort when we were thinking about this. Okay. So the main idea is again here that you consider the smallest sequence of events that converts A1 to AI to B1 to BI. It is very similar to this LCS kind of stuff that we did. Right. Of course, the best cases are obvious, right? Because if one of them is completely zero, then you have to, or the empty string, then you have to basically delete all of them, and the other one is and if the or you have to add all of them, whichever it is, so, which takes order k number of operations. But now let's think about it, this recursive way of thinking, right? I wanted to convert sunny to snowy. Okay, and our job is to output ed of 5, 5, right? What is the smallest number of operations which will convert SUNNY to SNOWY? Now let's look at it. How does the recursive thing happens? The last bit, if it is same, if the last bit is both y, then what can we say?
We just need to edit the first 4 of each.
Yeah, so we kind of say that, okay, the last bit of y, so I can completely ignore that.
Yeah.
And all I need to do is that I just change the first 4 of them, right? Formal proving, you should be able to prove it now, right? So if the last bit of y, you know that this is exactly equals to ed of 4, 4. Okay? But the next one is n and w. They are not same. Then what do you do? What can be done? What do you think?
Well, now we need to edit the first 3 and then add 1 because we are changing here.
Who told that the changing is the right thing to do?
Hello?
Who told that changing is the right thing to do?
Because N2W, oh, yeah, I don't know. I thought like.
Changing
But-
might be one of the options. So actually here there are 3 possibilities that you can do, right?
Yeah.
So we can choose the minimum.
Right. The minimum of what?
Minimum of the 3 operations.
Minimum 3
Like-
options. What are the 3 operations? Change n to w, delete n, and basically convert SUN to SNOW, right? Or add w and then try to convert SUNN to SNOW. And that is exactly what you do. That ED44 is basically ED33, which basically is change, or ED34, that means you delete n, or ED43, you insert w. And you add 1. And this is basically the recurrence again. Right? And now you can write a pseudocode of that. Simple thing. It's a recursive algorithm. I've not given you a full formal proof of this statement, the correctness of the algorithm, and so on and so forth. but by now you should be able to do it by yourself. Is the recurrence kind of clear?
Yes, sir.
Right. Okay. Now, again, you can see it that if you just do this recursive thing, it would actually become an exponential time algorithm. Okay, because it will become something like yeah. So I plus j can go down by 2, or it can go down by 1, and the worst case, right, is I minus 1j, and so this will become something like t of n equals to 2 of tn minus 1 plus t of n minus 2. Now this is not an easy recurrence to solve, but if you guys remember anything from your discrete math courses, you will be able to say that this is kind of like this Fibonacci sequence kind of stuff like that. And you kind of should kind of have an idea that this would end up becoming something like 2 to the power order n. To get the exact bound, you have to use kind of recurrence relations, kind of the generating functions kind of stuff. But I'm not going into it. So this is an exponential time algorithm. But again, once again, you should realize that this thing has the same thing being done a few times, right? For example, when you are here already, you can see that the next step of ed I minus 1j, if I minus 1j is different, there will be one term called ed I minus 1j minus 1, right? And that is same as what you do here. So there are again, of course, a lot of repetitions that you do in your computation. And hence, main idea is use dynamic programming. Again, I'm trying to drill this one into your head. I told you there are two things important. One of them is the fact of using recurrences to solve. Okay, this is one of the most important things of algorithms to kind of think recursive. This is not how a normal people think. Think recursively, and when the recurrence uses the same thing again and again, use dynamic. I mean, they're like very simple. And when you use dynamic programming, okay, of course, I mean, you can go over this whole drill again, that we decompose this problem into smaller problems, and you kind of combine them. And the main idea is store the results in a table. And that's how you do it. Okay. Fine. Now, how do you do this? Again, the recursion is there, right? So question is, what do you store? By looking at this EDIJ, you should immediately kind of come in your head that all I need to do is that you have to fill up the table of n cross m. And when I do this table of n cross m, you can see that at any time, the ijth entry can be solved by looking at the I minus 1 j minus 1th entry, or the I minus 1 jth entry, and the I j minus 1th entry. So, I mean, if you go over this whole thing, if you want to convert sunny to snowy, you write this table. You would like to fill in the base cases, and now fill it up. Now, maybe just as an exercise, can you guys quickly in your notepad and all solve this table, fill up this table, and tell me what is the actual value of this? What is the minimum edit distance of this? Hello, nobody managed to come up with a solution?
Yeah, three, even three.
It will be three.
Yeah.
Three only, right? Okay. What about the rest of you? Let me ask you a very simple and honest question. Please give me an honest answer. How many of you have not been able to fill up any of this? Any?
Sir, it's coming out to be 4.
Hmm? Somebody got
coming out-
4. Okay. Let's see. At what level you got 4?
In the last level.
Last one you got 4.
Yes, sir.
Why is the last one 4? Last one y is equals to y. Look at this. Last one is ai equals to bj. So it should be as the
Sir,
diagonal.
3.
Oh, sorry. Yeah. 3.
Sir, it's 3.
It's 3,
Right.
right?
Yes,
Yes, sir.
I mean, I don't know if it's 3 or 2 or something, but it should not be
Yes,
4.
sir, it will be 3.
So mine came out to be 3.
Okay. Has everybody of you got it? Or whoever attempted to get it, has you got it? Okay, I'm assuming that's a yes. Okay. So yeah. So this is the kind of the pseudocode of this one. And that is basically the simple edit distance kind of stuff. So now, as I told you, this is the kind of more like a tutorial class kind of stuff. So we will jump into another problem. And this problem is something, very interesting problem. And the reason it is very interesting is because, yeah, we will get to know about it more in the last part of the class course actually. But oh, okay. So the runtime of this algorithm was order nm, and why? Because every square of it was filled with constant number of, right? Again, you can also, if you want, completely produce the actual set of actual sequence of edits instead of just the numbers using the same kind of a dynamic programmability. Right. So let me jump into the second problem. This is called the knapsack problem. The knapsack problem basically says that you have a list of items. Each item has two parameters. One is a value and one is a cost. So thinking something like you are going to your home, right? And you want to take as many goodies that you can to your home. But of course, you have a suitcase, and that suitcase is has a limited amount of space, right? So don't think of it as kind of a it has a geometry to this suitcase or something. You think of that you have kind of a rucksack kind of stuff, something like a knapsack. And the idea is that what you can do. So the knapsack or the sack has a maximum volume, right? So that volume is a C. So what you can do is that you can take any item, but when you take that item, you of course have a cost associated. You have a cost of the value or value of that item. I mean, how important is that item to be taken, or what is the cost of it? But then also it has a volume, right? And that volume is taken up if you put it in that bag. You are not allowed to take a partial of any item. Okay. So you cannot say that, okay, I will take half of this item and half of that item. No, that is not allowed. You have to take either the whole item or not the item. And the geometry doesn't matter. It doesn't matter that whether there is some square or rectangle, is my knapsack square, kind of how can I hold it and all. All that matters is volume. Okay. Now the goal is to optimize or find out the what is the maximum cost of items that you can take home. Under the restriction, of course, that you cannot pack, the total volume of the items that you pack cannot exceed the volume of the bag. This is a typical what is called an optimization question. When the job is to optimize something, something that is used a lot of times in many places. Even simple things like, I mean, when any institute or a tries to organize some kind of a, say, some schedule, some exam and all those kind of stuff, they basically have to solve this knapsack problem. So the idea is that you want to kind of make as many people happy, as many people's wishes. You have to keep as many people's wishes, and yet you have to kind of solve under some constraint, right? So this is basically the generic idea. So I mean, here's some nice kind of a picture of this whole thing. That yeah, so this bag can take at most 15 kgs, and you have certain kgs, various weights and various of various volumes, and how much can you take? So is this problem clear? Or should I repeat it?
Yes, sir. Yes, sir. It's clear.
Okay. So I mean, so here is it. I say this item is. So what you have been given is basically a bag, capacity C, and the items item 1 to item n, and and each item, the item I has a volume I and a capacity Ci, right? And the goal is to pick a subset S such that the sum of the volumes is less than C of the S, and this is maximized. The sum of the cost of them all is maximized. So this problem is actually a very hard problem, something that you might have heard that term. This is actually an NP complete problem in some sense. If you are not familiar with this concept of NP complete, don't worry, I will introduce it later in the course. Maybe 3 weeks from now, or even just 2 weeks from now, we will be dealing with this exact problem again. But yeah, but still, okay, if I tell it that it is an NP hard problem and whatever stuff like that and all, a question is that what is the input here? Okay, if we are not worried about the bit representation of this kind of values of C and such things, then can you come up with an algorithm that solves this problem in some nice way? Let's say, can you think about it? Can you just make a first attempt? Of course, if at all, I will say that trick is to think recursion. Can you think about recursion? So please, I mean, I'm giving you another 5 minutes to think about it and come up and design a recursion that you can possibly help, which might help you to solve this problem. Okay, you can think that C to be a, I mean, the input itself is C. Okay, so you have been C, so you don't have think of C as a. Anyways, think of the recursion. I will explain this what I was explaining later. Okay, so let me give you 5 minutes to think about it and solve a recursion. Find out a recursive way to solve the problem. Hello, did you guys make any progress?
Can we do it this way? Like if we say D of C is the total cost collected,
Hmm.
D in bracket C, DC, then D of C is the maximum of D of C minus D1 plus C1.
And
Or-
thirdly, what is C here? You're not using the C capacity. Generic capacity X. D of X is the total. I didn't get you. Can you?
Yeah, okay. D of X equal to maximum of D of final capacity, means this big capacity.
Okay.
C minus D1
Mm-hmm.
plus C1. Similarly, like maximum of D of total this big capacity minus DI plus CI for all the I is equal to 1 to N.
Okay, so but see it. Okay.
And base case is C equal to 0,
So,
then
but the user if you are using, then it will be D of C equals to D of C minus VI.
plus CI, cost of that item.
Right. So okay, that is
This is a recurrence, and case case is that if capacity, big capacity, that capacity is 0, then D of 0 is 0.
right. So that's a good way of doing it. Yes. So the D of 0 is 0. D of C is minimum of
Maximum.
D of C minus VI plus CI kind of stuff, right?
Yes.
That is correct, but the problem that happens, can you see what's the problem that happens there? The problem is that once you have used, the first one you have used a minimum of something, right? So minimum over 1 to N, right?
Yes.
So say in the, so the minimum that comes out is that, okay, use the first item. When you go to this, so you'll go to this D of C minus V1. But D of C minus V1, you are again, it is a minimum over all possible items again, right? And that might say, oh, take V1 again.
Yes.
Another
Yes.
it should be there, like number of items.
Hmm?
Another argument should be added, number of
Another item will be added. Else, what is happening is that their algorithm might actually end up using the same item multiple times. Do you follow it? Hello, Luna, did you see?
Yes, sir.
Understand?
Yes. Yes.
Right. So if that is the reason why somehow we have to control every time when I'm adding something. Okay. And this is exactly what actually we will be doing. You are good that you came up with this. So we think of these items has been ranked as some order, okay, I1 to IN, and KSIC is the maximum cost of the item that can be packed for a bag of capacity C when you are allowed to use only I1 to II, right? Of course, again, the base case, I'm not worrying about it, that if you have no I, then of course the total capacity is 0, and if you have no capacity left, then total thing is 0. But most interestingly, what is IC, right? So IC, the maximum can be there about what, right? It's that, okay, I'm not going to, so there are two cases that can happen, that you don't use the last item, the II item. You don't use the II item, then I can say that, okay, then I can think of it as, actually there's something written wrong here written. it will be Ks. Oh, sorry. If you don't use the ith item, it should be Ks I minus 1c. Right? And if you use the ith item, then it should be, again, there's a mistake here. It should be Ks I minus 1 C minus Vi. So sorry, this is actually mistake. This is K minus, it will be I minus 1. Both of them will be I minus 1. So if you say, okay, what all items? Okay, there are two options. Either I take this item or not. If I take this item, my capacity goes down and I take this option. Okay. So in that case, this should be K of IC would be Ks I minus 1 C comma V plus Ci. And this will be Ks I minus 1 C. Okay, so there is a mistake here. This whole thing should be Ks I minus 1 C minus Vi plus Ci. So this is the case when you are picking up the ith element in the knapsack. And the other case is you are don't picking up the ith element in the knapsack. And that is it. And you can basically do the kind of knapsack problem in the same thing. Of course, I mean, I've jumped over here. And you basically have make a matrix. How big the matrix will it be? Can somebody say how big the matrix will it be? Hello? Am I audible?
Yes, sir. Yes, sir.
How big will the matrix be?
So there'll be n items,
Yes.
and
N cross C.
Yeah, it will be n cross c, right? There will be
N
n items in one side. First value takes first parameter takes n, second parameter takes 1 to c or 0 to c. Right. So total size of the matrix will be n times c, and you will be solving any entry using just looking at two of the previous entries. Right. And by doing so, you will be able to solve it. I'm not going over this whole thing there. So there are total number of spaces is order nm, cn. Each item requires a constant time to fill. So there's a lot of mistakes in this slide. So total runtime of knapsack is order nc. It's not LIS, it's n knapsack. Now, what does it mean? Wow. So this is something that will help me to kind of introduce to you to another concept. We have been telling from the day one that it's a polytime algorithm, linear time algorithm, exponential time algorithm, and so on and so forth. All of it is says that it is linear in what? It is polynomial in what? Whenever we say that, oh, this is a linear time algorithm, or this is a polynomial time algorithm, this is a quadratic time algorithm, they are linear or quadratic or whatever exponential in the input size. This is the key word that you should also get into drilled in your head. In the input size. Now, what is the input size in this case? In this problem, what is the input size? Hello? Akash Kumar Gupta?
W.
Sorry. Yeah, Uma, tell me.
Sir, isn't it the capacity?
Input size is the capacity? Just the capacity.
No, it's actually both of them, both N and C.
Okay, N and C.
But
Yes.
yes, sir, it should be both N and C actually.
It should be both N and C.
I'm guessing.
And why are you guessing? Just
No, because it seems too good to be true, because we are so far only used to input size like only N, right? So this one is like based on both the inputs. So I'm just thinking that's why.
I mean, we are not never guessed on only just inputs of N. we dealt with graphs, right?
Yes, sir.
The input was not just n. It was
Yeah,
weights
yeah,
also.
V and D. Yes, yes, sir.
No, there was weights also. The input can be weighted graphs. Weights are also inputs. Okay, everything is an input, by the way.
Yeah, yes, sir. Yes, sir.
C, VI, and CI, all of them are inputs. But that was not my main question. Mayank?
Yes, CU is a constant. So actually, back capacity is constant. So that will be actually n, I think.
Why is back capacity constant? Who told the back capacity is constant?
There is a lesser equals to C. So whatever we take, that total capacity will be less than C.
I don't understand that. I mean, C is something that is given. If I give you a bag of a bigger size, then you get a bag of a bigger size, and you live with that. So C becomes higher.
Okay.
Sir, C.
C.
Sir, n for n items we have size n input, and sir, its input also depends on C, sir. Like however big C will be, our algorithm's complexity will depend on it, like a pseudo polynomial.
Okay, I don't know what pseudo polynomial or any such thing, but you are saying that it is dependent on n and C, right?
Yes, sir. Yes, sir.
So the input size is n times C or n plus C, kind of stuff like that. A polynomial in n and C. Is it correct?
Sorry, sir, we couldn't hear you. Oh, what was that?
The input size is a function of n and C, of course. It's what is it? It is the upper bounded by n plus C, or it is n times C, kind of something like that.
Yes, sir. N times C.
N times C. Anybody it opposes to this?
So the input size is the size of input which we are giving.
Sorry?
The input size means the size of input, like the whatever input we are giving. The size of that
is the
input
size of
size.
the input we are giving. Yeah.
So sir, then would it be n? I mean, we are giving the value and the cost pair of the weight and cost pair of n items. So can it be n, sir? The theta
Oh,
of
you
n.
don't. So C is not an input.
No. Yeah. C is also input. Yes, sir. So that is one input only. So would it be n, theta of n?
No, why is it one input?
Sir, it is back capacity.
Sorry?
Because it is a back capacity and it is only
Why
one
is it
input.
one? I mean, if I give you a number and ask you, is the number a prime? Input is one. Size of the input is one. That's what you want to say.
Oh, okay. Yes, I got it. It would not be one.
Anything that is given as the input is an input, okay? But again, I repeat, input size. I have not told anything about the correctness of whatever you guys are claiming. But I want to see that this discussion has been done before also once. So Luna, you are saying something. You have some.
I was saying that there are total 2 into n.
2 into
as
n.
V1, C1, V2,
Right.
C2, that is 2 into n.
Yeah.
And then back capacity C is 1, then 2n plus 1 inputs.
So what is C? And what is input size? Okay, let me ask you, what do you think, Noah, what do you guys think about input size? What is an input size? What is an input size? So think of that you have written a program that given that you fit in a number and it will output you whether the number is a prime or not. You fit in one number.
So number of bits used to represent that number.
Number of bits. Remember this thing throughout your life. An input size is measured by the number of bits required to represent. Okay, input size is measured by the number of bits required to represent. Okay, if I tell you that the bag has capacity 1 million or say 1 lakh, then what is my input size? What is my input size?
Log 1 million.
Huh?
Log base to 1 million.
Log base 2 of 1 million. It is not 1 million. I will give you the bitwise representation, or maybe the digit representation, and each digit can have its own representation. That's a different thing. But irrespective of that, it will be order of log base to 1 million. That order will depend upon whether I'm writing it over alpha of the decimal representation or binary representation or what. So the input size of this problem is 2 times n times the number of bits to represent v1 to vn or c1 to cn and this number c, which is, we can think of that all of them, v1 to vn and c1 to cn, they are upper bounded by the size c, right? So it is 2 of n plus 1, 2 of n times log c, or in other words, input size is something of a constant times log n times log c. Is this clear?
Yes, sir.
This is a very important concept. Very important concept. I mean, this is something that we will be needing again in the next few lectures or few weeks. Very crucial. Something. Another important thing that you have to drill into your head. Okay. Anything that you give to an algorithm, to a problem, you feed anything, that bitwise size is its, what is the input size? Hello, oh, why bitwise? Why not decimal size? What happens if I write in decimals? Yes, if you write in decimal, it will be log base 10 of that c. You write it in bit, it will be log base 2 of this c. And you prove that log of 10 of c is actually order of or theta of log base 2 of this c. They are just constant away from each other. So they are not that too much different. But log is important. Log base some constant is that, what is that important? Okay.
Hello.
Yeah,
Sir,
hello.
Sir, this CI is less than C.
I mean, think of them CI to be less than C, all the CI to be less than C.
Okay,
Else you have to take the maximum of the CI kind of stuff like that. Okay. But again, this is not something about what this, I mean, yeah, the issue is that, yeah. So it will be actually, rightly speaking, the size of the input will be log of C plus log of V1 plus log of C1 plus log of V2 plus log of C2 plus log of Vn plus log of Cn, which will be log of C into V1 to C1 into V2 into C2 into Vn into Cn. Okay, so which will basically become something like n times log of something. It will be n items and it will be that. Okay, so technically the correct input size will be log of all of them added. So now I come back to this question, okay? So this problem, what I presented here, the knapsack size can solve it in order n times c input size is, okay, it's written n plus c, it's not, it's n times log c, but doesn't matter. But n times log c, and this is n times c. So if the c is very small compared to n, then this is fine. If c is something like polynomial in n, then this thing is polynomial in n, which is a polynomial in the input size also. But if the c is big, or in other words, the general c is not. So therefore, we have presented an algorithm using dynamic programming for the knapsack problem. The runtime is ordered n times c, but doesn't mean this is a polynomial time algorithm. This is actually an exponential time algorithm. Is this clear? Hello, should I repeat this thing once again?
Sir, I don't know why, because this thing just kind of confused what all we've learned before also. Because before we used to say inputs were n, right? Like input size was n. And
Yeah.
now we are getting something like log c out of the blue. It's at least seeming to me as if it came out of the blue. Like, why aren't we using c, and why are we concerned about the bit size now when we were never concerned about this before?
We are also concerned about the bit size now. Okay?
Even
Earlier
before?
also, we are concerned about the bit size also. Okay. So think about it. Actually, when we told that the number of steps was, we told that the number of steps or time complexity. We talked about the time complexity. Okay. Time
Sure.
complexity, we wrote it in terms of n and m. Okay.
Yeah.
Fine.
Yes, sir.
And we kind of told that, oh, this is linear. Okay. Now, what is the input size of a graph? Think about it. Okay. Input size of a graph is n plus m plus we have this kind of, okay, of course we have to give the bits and all those kind of stuff, the kind of referencing and all those kind of, whatever, the pointers and all. And what will you go and calculate what is the bit size representation or bit size input size of a graph. Okay. And I mean, I will let you guys think about it. Okay. So,
Sir.
yeah, hello.
Yes, sir. Yes, sir.
Yeah. So that time, at no point of time, we dealt with something which was one mass, which was representing a huge number. And never did we did that. Okay. Never did we do that. So let me give you an example of this. Okay. So do you guys use credit cards? Hello? Do you
Yes,
guys
sir.
use credit cards? You do, right?
Yes, sir. Yes, sir.
Oh, excellent. So do you use it online?
Yeah.
Why is it secure? Why do you think that somebody cannot hack into that whole thing?
I have very vague idea, but given the bit size encryption, it's very hard to break into that.
And crucial part of this whole thing is that if I give you a number, I can give you an integer and ask you to factorize that number into its prime decomposition, that is very hard. Okay. Now,
Yes,
if you think of a number as a number, that's it. Okay, you give me a number. Yeah, I will take that number, say 1000 or 1059. I don't know. And I will go over all the integers from 1 to 1059. Right?
sir.
And divide it, and I keep on finding all the prime factorization, and I'll be done with it. Right? So it is very easy to factorize a number. Did you understand the algorithm? How to factor in the number? You have a number n, you go from 1 to n, all possible numbers, and you check for 1 to n minus 1, and you check which of them divide. Division is an easy algorithm to solve. And by doing so, you are done. The reason that is hard is because encryption that is used is a massively huge number. Okay, it's a prime, it's a number whose size is of the order of something like a few hundred. Sorry, a few hundred digits. Okay, so the number is a few hundred digits. Number is something 128 digits. So what is the number? It is as large as 2 to the power 1 over 128 digits. Input that you place is the 128 digits. Input is the digits that you, number of digits that, or the bits, whatever you want to call it. Okay, and the algorithm that I gave you depends on the number actually, and it is exponential. If you say that, oh, any number, any integer that you give me is one integer, then anything can be done easily. Right? So everything that we have told so far, either we have made statement like this, that the number of comparisons is order n square. There we did not talk about time complexity or any such thing, number of comparisons, or order n log n and so on. That is in the case of sorting. Or for the case of graphs, we told that the number of steps that you do is order n plus n, kind of stuff like that. There also, we did not talk about the two things that we kind of brushed under the carpet. One of them was how much time does it take to read a pointer, and equivalently that same thing. What is the space of that whole thing? The space is n plus m, or n plus m only. This because for a graph, the number of entries of things are n plus m, but you have n plus m possible pointers, and each pointer takes another log n space. Okay, so although we have not talked about input size as a bit representation when we are dealing with those things, one of the reasons was that, I mean, we did not talk about the bit representation in the input size, or sorry, in the input also, neither in our algorithm. And you go over it and you find out that there will be same thing. But in this cases, particularly when there are numbers involved, there are integers involved, things becomes a bit more crazy. Okay, so you have been, so at this time, the input of a size log n, or a n bit, or rather an n bit input equals to a 2 to the power n size number. And that's why in such situations, it is very important to look into input size. Did I make something clear or not? You guys are even more confused.
That credit card example kind of is making sense now, but yeah, yes, probably I'll read it over once so that it will be clear. But yeah, I am kind of getting an intuition of it.
Okay. Okay, so anyway, so now, so what did we do today? So we have done, we were looking at dynamic programming. We looked at edit distance. and we gave you a solution of the knapsack problem using dynamic programming that is not the polynomial time algorithm in general, is something to note, but it is still an interesting algorithm. This will be, I will not be doing more of dynamic programming in the next weeks or so. As I told you, the next week I'll go back to some very basic graph algorithms and some other greedy algorithms kind of stuff before I jump into a completely new topic, which will be more, I mean, to some level more interesting. It's using the reductions and all, something that I've been moving towards last. So one thing that I will kind of give you guys as a problem to think out, or for one assignment will be uploaded very soon, but is that in the last class I dealt with this LIS problem, like longest including subsequence, and I showed you how to reduce the LIS problem to LCS problem and solve it. And that gave you an algorithm of order n square. Now, think about it. Can you come up with a better algorithm? Okay. Hint again, dynamic programming. Using dynamic programming, try to come up with a better algorithm for the LIS problem. So think about it, and this problem will be there in the assignment. And okay, so that's it for today. So if you have any questions, you can ask, else we can end this session.
Sir, in the
Yeah, go ahead.
in the previous slide,
Yeah,
that here if C is small,
yeah,
C is very small,
yeah.
then n log C is very small, so that's why it is
So-
like n to the power some fraction.
Now this C is very small, meaning say C, the C itself is of size say n to the power say n square. Okay, let's say C is of this order n square. Then what is this one? This is order n cube,
N cube,
but the input size is n exists, right? N times log C. So log C can become nothing more less than 1, it can become, right? So the
yes.
input size is more than n. The input size is more than n. The dynamic programming will give you a solution of size n cube. So it is polynomial in the input size.
Oh,
Okay, but if C is massive, then this log C will start dominating n. So think of C to be 2 to the power 2 to the power n. And log C is 2 to the power n. So the input size, this n is like nothing. It's nothing compared to this 2 to the power n that will be sitting here. The input size will become 2 to the power n. And dynamic programming, it will be n times, again, this n is like nothing. 2 to the power 2 to the power n. So basically, it will be that the time complexity will be 2 power the input size.
okay.
Okay.
Sir,
Yeah.
like what makes both these algorithms exponential time? Like even though we are storing previous computed values?
Because the size is C, I mean, because this side is C, right?
Ah, yes.
Size of this whole size of the this matrix is C times n, right? That C is itself is exponential in the input size.
Then in that case, what about the edit distance problem?
The edit distance, what was it? What is there a C? What was the input size? Tell me.
n, right?
This is the n, because there is no kind of no hiding about it, right?
No, not in terms of bits and other things. Like 2 power order of n is the thing, right? Yeah.
So that is the recursive algorithm when we are not storing.
Okay.
This is just the recursive algorithm when we are not storing. Okay. But when we are storing, then the time complexity goes down to here, order nm.
Okay. Sir.
Okay. So you make a sudden jump from exponential to polynomial by just storing the data. And that is basically the trick of dynamic programming. That's it.
Okay.
Okay. Okay. Any other questions? Okay. So if not, let's stop the class now.